Most derivatives are pretty self-explanatory, or at the very least, easier to remember. When I took my first calculus class, I remember smooth sailing through most of the derivatives. Okay, so I understand the power rule, e to the x is always equal e to the x, and sine is cosine, and the other way around is negative. It was all pretty simple, until one day my teacher gave this paper to me. What is this? It's a pretty sudden jump, and it's a lot to remember. But today I hope to clear up some confusion about the derivatives of inverse functions by showing the proofs. So there are 6 inverse trig functions you can take the derivative of. But you'll notice that these 3 are just a negative version of these 3. These negative versions actually have the exact same proving methods as the positive version, so you only need to know the process of 3: inverse sine, inverse tangent, and inverse secant. So those are the 3 I'll be going through today. Let's start with the derivative of inverse sine. Now to begin this proof, let's set up the equation like this: y equals inverse sine x. Our main objective is to have an equation like this: y prime equals something. Now that something has to be in terms of x, so that's what we're looking for. So to start, let's make the inverse sine into a regular sign by switching the x and the y. So we have x equals sine of y. Now at this very moment, I want to introduce the most important tool to help us with all these proofs: the right triangle. You might remember this from the SOHCAHTOA days, but sine theta equals opposite over hypotenuse. And these are the elements we're going to label on the right triangle here. So we know what theta is, it's y, so the y goes here. Now since sine y equals x, we can technically say that x equals x over 1. So then the opposite in this case is x, and the hypotenuse is 1. So we label that all, and once we've located these points, we come back to the sine y equals x equation and take the derivative of it. So since we're taking the derivative with respect to x, the sine y becomes cosine y, but we also multiply it by y prime because of implicit differentiation. Now the other side is just the derivative of x, which is 1. Remember, the objective was that we wanted y prime isolated. So we divide cosine and we get y prime equals 1 divided by cosine y. But we're not done yet, because we still have this pesky y that we have to get rid of. This is where the triangle comes into play. If you've noticed, we actually went from sine y to cosine y. So the theta is still the same, and we're actually using the same exact triangle. That means we can use this triangle again using SOHCAHTOA to get the cosine. Now cosine is adjacent hypotenuse, and the adjacent can be found using the Pythagoras theorem. So we set the Pythagoras theorem up: x squared plus b squared equals 1 squared, and we're trying to find b. So we isolate b and we get the square root of 1 minus x squared. So that is our adjacent, and we divide that by the hypotenuse, which on this triangle is just 1. So that is what cosine y equals: the square root of 1 minus x squared. For the last step, we just have to plug this value into the y prime equation, and we get y prime equals 1 over the square root of 1 minus x squared. And that's the derivative. On the derivative sheet, that's what you'll see, and the cosine proof is pretty much just like that, except when you take the derivative of cosine y, you get negative sine y, which is why there's a negative. Moving on to the tangent proof, you can actually try this one out for yourself. It's pretty much the exact same method from before. So for this one, we want to make it tangent y equals x. So now let's note the points on the triangle. We'll choose this angle as theta, and so the tangent is opposite over adjacent, so it's x over 1, so x is the opposite and 1 is the adjacent. Now we take the derivative of both sides, so we get y prime times secant squared y equals 1. We then divide this to get y prime equals 1 over secant squared y. Now since the reciprocal of secant is cosine, we can actually just convert this to cosine squared y equals y prime. Going back to the triangle, we see that cosine would involve the adjacent and hypotenuse. The adjacent is 1, while the hypotenuse is 1 squared plus x squared. However, since cosine is squared, there's actually no need to square root this equation, and so we just get a final answer of y prime equals 1 divided by 1 plus x squared. And that's our tangent proof. Now for the third and last proof, it involves y equals inverse secant x, a very spooky looking function, but it's the exact same process. We turn it into secant y equals x, and we drop the sides. Y is theta, and this time, since it's secant, hypotenuse over adjacent. So the hypotenuse is x and the adjacent is 1. We then take the derivative of the equation, which would be y prime times secant y tangent y, and that all equals 1. Then we divide secant y and tangent y to isolate y prime, and this gives us 1 divided by secant y and tangent y. We can then rewrite this as cosine y over tangent y, and so let's start by finding cosine y on the triangle. The adjacent is 1 and the hypotenuse is x, so it makes it 1 divided by x. And now for the tangent, it's opposite over adjacent. The opposite can be found by using the Pythagoras theorem, 1 squared plus b squared equals x squared, and this results in b equals the square root of x squared minus 1. So since the adjacent is 1, the square root of x squared minus 1 is our tangent y. Now we have an answer of 1 divided by x divided by square root of x squared minus 1. The 1 over x can combine on the denominator to get a final result of y prime equals 1 divided by x times square root of x squared minus 1. And those are all the proofs. Congratulations if you made it this far. It's really just the same process over and over, but just remember the triangle. That tool is definitely your best friend. Hopefully this helps. Best of luck with your studies, and bye bye.